All right, I do hope that is showing for everybody. Can I get a, yeah, okay, cool. Thank you. I saw some thumbs up. That works. Um, I'm hopefully going to piss a couple people off with talking about this stuff. Um, but I want to give you a little background on me that some of you may or may not know. There we go. I grew up an engineer. Back in those days, I was working on fixing TVs at 5, 6, 7. It wasn't exactly difficult to do. My mother was the first female engineer at NBC during World War II. My father worked on radar systems and all sorts of stuff with Bell Labs, MIT, and then in the Navy. And down at the bottom on the left, that was my local, when you wanted to build something or make something, that was our local electronics store, which is kind of cool. And on the right was the first analog computer I ever built. And I was at the great age of, I don't know, maybe 8. Not exactly difficult to do a little bit of soldering. So the point is that all of this was an analog world. And I really grew up with that mindset and ended up later on in the audio industry, so-called the family business, if you will. And basically, it was a lot of systems that all had to work together and to produce, in this case, records. The thing up in the middle is an old mastering lathe from the mid-60s, and it was a combination of analog audio and then heavy mechanical systems as well, and it had an ICS component to it, even though we didn't call it that back then, nor did I have any clue what that was going to be or how it was going to maybe have an impact on my future career. But this is the world that I grew up in. And then I found security in 1983, back in Orange Book and all that other stuff. And I did a bunch of security stuff, if anybody cares, and I've been doing it for a long time. And as a result of all of these years, I've come to really believe some fundamentals about security that we don't talk about a whole lot. And we talk about, okay, what's the next generation thing that's going to fix it? Oh, we're now going to make our AI MLDL. It's going to be a better, yeah, okay. But none of these really are addressing fundamental concepts of what security is, should be, how does it behave, how does it integrate and become part of the cyber human experience, which is what this really is all about. So one of the questions I asked on one of the COVID talks, so I think some of you may be on those talks with us on Fridays, is what's security? And that kind of shut everybody up. What is security? Can we define it in any real, meaningful way other than these sort of abstract things that, well, is your system secure? Yeah, it's secure. Well, how do you know it's secure? Well, it's, and we play these fudge games because we don't know. What does secure really mean? And does the word secure, does it translate from one environment to another, one enterprise to another, one working environment, an ICS environment, SCADA, or cyber? Do they all, does secure mean the same thing in all of these cases? And I have come to absolutely believe, no, it's not. We need some new terminology and some new ways of thinking. And one of the things that I don't hear talked about much is that security is really an arbiter of trust, or trust is an arbiter of security. It depends which way you want to look at it. And that's because in order for any system to exist, it has to have more than one piece. It's got to at least have 2 pieces. And then you have a relationship, even if it's only 2 pieces. I've come to believe that defining that relationship is a lot more meaningful than trying to say any one piece somewhere in an enterprise is or is not secure, because the term I think is really very misleading, and it's unfortunate that we hear that so often, all the way from politicians and executives. Well, am I secure now? Am I safe? And that question is, I'm arguing, very meaningless, because it's about trust and relationships between objects, subjects, to use some of the early technical terms from Orange Book, Red Book, Anderson model, the fundamental works that were done back in the 1970s. So I asked myself a question, or I'll ask you, and I think we can do feedback here. Yeah. All right. You're going out and driving. How many of you by a show of thumb ups, are absolutely 100% positive you're not going to get into an accident? I got some people are either laughing or holding their heads in disgust. It's very difficult to tell, but I'm wearing the wrong class. Okay, I'm seeing a lot of heads. And obviously, hopefully not, but the odds of an accident is somewhere between it ain't going to happen, or it is happening, or has happened. But can you predict it? No, there's absolutely no way. Therefore, when you leave your house, it's somewhere between 0 and 1. You're not absolutely sure you're not going to be in an accident. You're not absolutely sure, unless you're insane or psychotic, that you are going to be in an accident. And that's a whole different talk. So airplanes, I know we all used to be in airplanes. Remember airplanes? Hello. And were we absolutely sure the plane wasn't going to crash? No. The odds are, statistically, probabilistically speaking, it's really been safe for a long time, barring some couple notable unfortunate events. But how can we be 100% sure? Now, some people you see on airplanes, they cross themselves, and some have 7 vodkas before they get on in order to establish or feel comfortable with the level of trust that we have in the pilot, the machinery, the guys that close the doors for the baggage, all the system components is a matter of trust. Same thing with COVID. Is there any assurance that absolutely I got 2 vaxes, I got the booster, and am I 100% sure I cannot catch it even though I'm really, really safe? No, I'm not 100% sure. So I modify my behavior a little bit to increase the odds, because there is no 0 and there is no 1 in this at all. How many of you would not take this ride? Let me see, either thumbs up, downs, or I hate it, or I'm getting nauseous. Yeah, I don't think I would do that. Now, in terms of safety, boy, I'm not sure that I'd be anywhere close to, I'd probably be closer to 0 for me personally. But again, these things exist, and we trust rides, we trust roller coasters, we trust the Tower of Terror and all of that the systems will operate correctly. So, can trust be absolute? And I argue absolutely not. We can not have 0 trust, because if we have 0 trust, we have no relationship. And without having a relationship, what's the point of what we're doing for a living anyway? What's the point of security? What's the point of systems? So 0 is absolutely meaningless. But 1, absolute, total, 100% trust in any object or relation between objects is also unachievable, because it is not falsifiable. You cannot prove the opposite of what you're trying to assert in the beginning. And it's just, logic kind of 101. So trust is somewhere greater than 0 and less than 1. And that puts it into the non-deterministic way of how I've come to view security. So trust is about relationships. And I use the trust over risk, 1 over risk, as an easy way of converting back and forth, because once you get the numbers and the system that you want to use, you can move it back and forth very, very easily. So whether you want to look at it from a risk standpoint, it's ultimately still trust, because risk requires relationships as well. But the cool part about all this is it really comes down to some math that makes security. I've argued since time-based security back in the late 90s that we need metrics. We need some common metric to be able to figure out what are we talking about and how much math is really about there, is available for us. Everything in our lives is an approximation. So when we hear the idea of digital audio, well, digital audio converts into analog audio through the various systems and acoustics, and so because our ears are analog, even though we may store it in a digital format. We hear the ideas of perfect square waves. There is no such thing as a perfect square wave. Doesn't exist, cannot exist. And again, the idea of approximation becomes so critical when we're thinking about security and how to implement some of these technologies. So when we look at physics, It's really pretty simple. In classic Newtonian physics, it's deterministic, and that's represented by A plus B equals C. It's a deterministic number that can be repeated and can be used if you understand the environment completely in a Newtonian sense. You can predict the future and you can re-examine the past, because if we have control over that macro environment, we're going to be able to do that prediction within given levels of tolerance, because everything is ultimately an approximation. At the quantum scale, we have an inequality, and that inequality is Heisenberg's uncertainty principle. And it doesn't matter what it means, but it's an inequality that it has to be greater than or equal to a given number based upon all sorts of crazy physics stuff. When I look at time-based security and the original work we did, it was 25 years ago now, it too is an inequality. And that inequality is because we can never be absolutely sure until we start invoking some common metric between them all. When we look at quantum computing, that's probabilistic too. And it gets even worse because right now we have to operate it in really, really cold million micro Kelvin scales, because noise interferes with the systems, thermodynamics, what have you. And we need to find ways ultimately to make quantum systems much more reliable and with a lot less error. Increasing the probabilistic answers are going to be statistically important, valuable. I apologize. So right now, all probabilistics with these machines are based upon greater than 0, less than 1. Purdue has been working on some interesting stuff with probabilistic computing, under the premise there is no such thing as a 0, there is no such thing as a 1, whether you're looking at the macro scale or the quantum scale. And I argue the same thing for security. Why aren't we looking at it this way? The human brain, our entire processing, it is all a probabilistic averaging machine. Some of us see better than others, don't require. So that means our granularity and the fineness of that measurement is better in some people than other people. I'm colorblind to a certain extent, so my sensory filters are not as good as somebody else's who is not colorblind. So this is our entire processing. Everything we do is an averaging machine with the hope, similar to Newtonian mechanics, to be able to predict the future. That is what survival is in any sort of organic system. We average our environment, we sense a whole mess of stuff, come up with an answer, and take an action in our own best interest. Again, probabilistic averaging machine. So some of the neural networks that have been coming out are very, very similar. They've done different types of modeling, and they're trying to mess with brain correspondence. And is it the same? Is it not the same? And so there's lots of different types of neural networks, but they too are probabilistic. You may recall the Microsoft racist Twitter bot 3 years ago. And I'm not indicting Microsoft because, everybody's experimenting on this stuff. And they put it out there. Within 24 hours, it was just like a racist maelstrom. How'd that happen? It got poisoned. It got poisoned by enough people of saying the same sort of hateful stuff that skews the probabilistic answers and predictability algorithms inside the networks to be able to, this is what they really mean. And so there's tons of examples of this in all sorts of search engines and algorithmically based outputs. The other thing that's interesting is when you're involved with these networks, you ask it a question, and then a few minutes later ask it another question, you're going to get probably a different answer. It's not going to be exactly the same because the neural networks are constantly changing probabilistically based upon the input that it gets. So when we hear companies say, I got AI, yeah, no, there is no such thing as AI. It doesn't exist, may never exist, and you can't even define what AI is, sorry. But we do have machine learning, and we do have deep networks, deep neural networks, and we've also got CNNs, convolutional neural networks, which are really cool because That's how Go got trained. They took a CNN here and a CNN here, fed them both the same rules, and said, you go first. And billions and billions of games later, it taught itself how to outdo humans in Go. Do we know how it did it? Nope, not a clue. Did it work? Yep. So we're using a lot of these types of probabilistic, deterministic determination machines to make decisions for us without understanding what's going on in the inside, which lends further probabilistic unknowns into any decisions that are coming out. So the real thing you have to come up with is this stuff really good? Yeah, it's really good if good is good enough for your answer. What's the granularity? How much accuracy do you want? Is it okay for English to French translation for tourists? Yeah, sure, spot on. Google Translate, spot on. Unknown pattern recognition, spot on. But you still need to have some sort of human construct on the back end of it to be able to finally do a higher probabilistic assertion of certainty of what you're trying to achieve. So everything that we live in is probabilistic. Now, in this case, which is more accurate? Yeah, who thinks digital is more accurate in this case than analog? Show of hands. 1, 2, 3. Okay, I got a bunch that think digital. Who thinks the slide rule is more accurate than the abacus? All right. After this talk, you guys go to a room and fight it out, because I vote for the abacus because of the number of significant digits that I can have there. Versus on most slide rules are good to 10 to the -3 to 4, but that's another argument. So at any rate, different ways of looking at the world, which is close enough. We used to send rockets, develop all this old stuff with analog, the guidance system, sure, for Apollo, all analog stuff. We had an entire analog computing industry, because it offered a really, really high speed, close enough answers for the right applications. Is it universally perfect? No, but it does have its place. So, is your network secure? Nope. We all know that. Now, I'm not going to go through all the heavy maths with you, but the point is I want you to see that this is all based in the issue of math, and that it is repeatable, and it is configurable, and it is designable, and you can architect around it. So in order to have a network, you have to have at least 2 nodes, and then you have to establish levels of trust. So one of the things that I use as an example, just for back in your brain, I bet you all trust your spouse. Yeah, okay. Do you trust your spouse with your life? I saw only one heart go up, only one thumb. Would you trust your spouse with your life if your children's life was at stake? Oh, well, I got one thumbs up. He hates his kids. Okay. Again, these are all answers that are going to be dependent upon the nodes. Each one is going to have its own answer. So how do we decide in these nodes, how do these work? And it's basic, simple probability that we can determine. And in our cases, let's talk about detection. Very simple. We want to know, can we detect something? What's the probability of it? And what's the probability that it's really happening? Blow the math. I'm not going to bore you with it all, but this is how it works, based upon trust. And so these trust factors up there, okay, the vendor says it's 99% accurate, which he's giving it a 99% trust factor, or 1% risk that it's not going to be right. And when you take a look at all the numbers, you can derive, based upon their initial claims, some idea of how it's going to perform over time. And then you can insert other variables as well into the into the equations. The thing that this is all based upon is stuff that goes back 70 years, and it's called a rock curve, and it's based upon radar and determining how accurate the symbols are. I'm sorry, the pinging. And I'm not a radar guy. My father was. Is how accurate is the signal, and how close can I get to figuring out where it's from? And so in our world, we have these four options up there. We have true positives in the red, and that's really what we want. That is the goal. And when a vendor says 99%, you got to figure out, what is he talking about? 99% of what? And becomes much more interesting to figure out what's a true positive rate, what's the true negative rate, and then what's the false positive and the false negative rate. And this determines what your ROC curve will visually look like. And where you want to be is, you want to be aiming up towards the upper left-hand corner. I know Gartner does it the other way around, but this predates Gartner. And these are the numbers that suddenly become much more important than a vendor. 99.2% of what? Show me how your probabilistic distribution is going to work in the real world. Show me your tests for the last 5 years. Show me something that gives me the beginning so that I can then plug it into my probability in my own equations for my own environment. Unless I know how you're working, I really don't know a whole hell of a lot. So when you look at, in this case, a very simple network, 3 nodes, look what happens. A, down in the lower left, he is a really trustworthy guy. They're great. They're good. And then B and C individually, yeah, they're pretty good. Not as good as A, and that's all trust factors. But look what happens when you start doing the math. When you start applying the probabilistic math that I showed on the prior slide, you end up with the trust relationships and how strong those trust relationships are between them. And again, the math is not terribly complicated. And look what happens when you've got interdependencies. And so we look between B and C, and this depends upon who is the primary and who is the secondary of the in evaluating trust. So it's not necessarily going to be trust symmetric, and you'll, in all the math, the time symmetry that exists with trust does not translate. So we have to look at it in both directions, and we take all of that, and what happens to the entire network's relationship? Now it's down to 52%. So what does this tell us? That tells us that we need to work on our trust relationships specifically, and the ones that are harmful in this particular case significantly are those between B and C. And that's where we can start looking at trying to get some improvements to overall raise the trust value of our network. Lots of ways we can do this. And in this case, looking at it from a hiring standpoint, hiring the unhireable. You've probably seen some of those talks I've done. Do you want the guy who's never had a chaotic moment and his firewalls and his configuration and security has always been perfect, or do you want somebody who's been through hell a few times? Do you care about whether he has a bachelor's degree or does he have certifications? And how important are all of these things? And this will help with some hiring in general, I hope, because we're having such trouble. And then you want to weight these. And in this case, it is regards to people and hiring and how much trust you can imbue in them. And this is only a starting point. On day one, when they start working, you have to have some set of numbers to be able to build that trust factor into a couple of things I'm going to show you. Now, keep in mind, trust is not binary. It's going to change over time. There are curves, there are degradation curves of trust, and I'll show you how those work. But everything ultimately, this emulates a simple neural network with feedback. That's all it does. It's very, very simple. In this case, using weighting factors to come up with a probabilistic means of the trust factor of a given object or subject. So in the two-man rule, you have 2 administrators, and what happens? If either Alice or Bob, even though both of them are really well trusted, can make the same change in a given system, either one of them independently, what happens to my overall trust? And that math is down at the right. Your risk has almost doubled. That's just the way the systems are and the math works out. And so if you end up with multiple people that have certain types of access to the same system, and it's a high risk system, a high value system, the individual trust value of each of those individuals becomes almost meaningless as you start looking at them as a group object, and the probability and the trust factor goes way the hell down. So we can do the two-man rule and go, yeah, okay, well, I require both Alice and Bob to agree, and you're going to get much better numbers as you see down there. That increases the trust factor significantly and decreases risk. In this case, though, because of time, A and B both have to agree. And how long does B take? Is he out to lunch? Is he away for the weekend? Is he on holiday? So what we do is we do a feedback loop around it that's time-based and say, okay, Bob has to confirm or deny what Alice wants to do within X period of time, and done. That's it. That gives us a whole set of new numbers that we can know exactly based upon the time of the feedback loop of when Bob must either agree or disagree with Alice. And that can be humans, that can be code, that can be network connections. It doesn't matter what it is we're talking about. These are all subjects and objects that have abstract mathematical values assigned to them. And we just calculate away. And the numbers are there, and it's going to change over time, and it's going to change all the time. And that's where detection and depth, how many sensors do I have in my network that I can add into my weighting? And am I going to have neural nets everywhere along the way? I don't know. That becomes some really deep architecture later on, but it's certainly possible to do this at a neural level throughout the entire process. Now, probabilistically, we want to see what happens over time. Obviously, I want my security to get better over time. And there's different types of curves here that show what security actually looks like. And we have to have the degrading curves, and those come from number one, a guess, which is what Bayesian probability does, and then taking the feedback loops into consideration, which will then adjust automatically based upon the range that is set of the degradation of the trust over time. This also makes it fairly simple to start understanding and visualize who's winning and who's losing in our cyber battles. And it becomes pretty straight ahead. Again, the math is simple. You got to be faster. You got to be faster than the attacker, period. If you are faster than the attacker and you can do your stuff, defensive detection reaction stuff, faster than the attacker can do his stuff, whatever that may be. And I know we have knowns, unknown knowns, and then unknown unknowns, which really sucks. If you can be on that left picture and be inside of your adversary's OODA loop by doing things quicker, you win. That would be the closest way to identify that you have a secure environment. However, it's so dynamic, and because of unknown unknowns, we'll never actually reach that absolute certainty. And it's going to be more like along something of the next two curves, that it's going to move all the time, but you're going to be trying to approach zero. So you don't need to know all the math, but you need somebody that can start thinking like this and start doing the calculations and analyzing your networks right now, because that'll give you an entirely different perspective as well as to where it needs help. Your takeaways: nothing. You're never going to get secure. It's never going to be number one. But you can calculate, and you can create some initial conditions and assumptions by which then you can continually monitor and measure your network performance, behavior of the systems and the people, or whatever whichever component you're trying to do, and look at it as relationships versus individual objects. It's how these things talk to each other that becomes so critical in evaluating how much trust you've really got. And finally, I love this analogy, and it's an old joke. You probably heard it. Two guys out hunting in the woods, and they see a bear, and one guy starts, run, 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 and the other guy says, yeah, yeah. And he sits down and he changes out of his big hiking boots into some snow fast sneaker technology that he has. And the other guy says, what are you doing? You got to run. You got to outrun the bear. He goes, no, I don't care about outrunning the bear. I care about outrunning you. You can do all this stuff now. You have the ability to start looking at these things. There's a lot of publications. A lot of them are mine, free, for anybody that wants to play and start taking a look at some of these theories and trying to see how they work. Start small, grow it up, and buy my book, please, because there's a lot of answers in there. Buy those books. Well, they're free, so you can buy them anyway. And that's it. Thank you very much. And I don't know how we answer or ask questions in this format right now, but I will do whatever I'm told to do. Rich?
Rang. Yes, thank you for that thought-provoking talk. Appreciate it. Folks, if you wanted to win some questions, you have the ability to type them in to the chat window on the right side on the menu. It's on the little purple square with the chat symbols in it. So Win, we have one there. Can you see it, Win?
I am looking up
alert from Google Chrome.
Oh, shut up. At least it waited till I was done.
Well, was there a 0 or 1% chance of that happening? So Mark Peavy made a comment here. Perhaps you want to
you read it. I'll
So Win is 100% dead on. You like that part right there. Regarding A, we don't have real AI active anywhere today, although ML provides neural automation capabilities sorely needed for WAN and security tuning. And B, security is indeed all about probabilities. But certainly deployable distributed cloud-native ML-based SASE platforms can certainly aid in managing the enterprise risks. And
yes. Only thing I would say first is, yes, absolutely right. But you really need to sit down and get a couple of your C-suiters on board to be thinking that doing an initial analysis and taking a piece of your environment and looking at it through this kind of lens before going out and deploying anything. But ultimately, the technologies that are available that you can get, I mean, AWS, is that ML system going to be good enough? I don't know that answer. I assume that a lot of the stuff is pretty tunable. Then you've also got so much open source AI code out there these days. If you want to, AI code, sorry, AI-ish like kind of code, you can play with that as well. What was it? The AI the version 3. What's the name of that just came out a couple months ago? Yeah, I'll figure it out.
No, that thing, yeah.
Yeah, that thing. I just completely lost the acronym.
Yeah, where do you think we're headed with quantum, if I may ask? Because that's something that's
boy, when you get into that, it's like, is quantum all that? Is it capable of? Is it capable of solving real world problems to the extent that some of the proponents are saying? And I would argue no. I think the quantum computers, if they can optimize the performance and they can actually put enough of these things together, whether they're going to do it optically or there's different technologies they're playing with, I think it's going to have some very, very specific applications for specific problems that it'll probably do pretty well with if they can solve the engineering issues behind it. But it's not a panacea. Again, it's an averaging machine, and what our world tends to do is deal with data, massive amounts of data, and that data is going to have to be somehow either treated in another form or converted to something that's really going to make a whole lot of sense to get an AI-ish, or I'm sorry, a quantum-ish output. It's been hard put for people to come up with cases, model cases that say, yeah, that's really great. I think it's going to be fairly limited. I would really like to see more of this work that Purdue and others are working on with analog computing. because of the sheer speed of it. It's almost, and I hate to use the word instantaneous, but it is a lot faster than running through circuits, than traditional digital circuits. So I'd like to see more research there.
Great. By the way, thanks to Bernard. He posted a link for quantum keys for security. It's in the chat window for those of you who want to follow up on that. Thanks, Bob. Thanks, Bernard. And then Bob, who's going to be speaking after the break, Bob Gorley, who is a friend of ours, he's got a question for you. I'll read that to you. What advice would you give the C-suite regarding protecting data? I'm not looking for the old ideas like MFA and patch your stuff, which is important, and you better be doing that. But what can we do that is new and different and really makes it hard on the bad guys?
Boy. You have which way my broken hands. You have a curve there, Bob, and you're trying to get me. You're trying to box me into something you're not going to do. You make it harder for the bad guys with today's available technology. You're going to make it harder for the good guys too, and then the good guys are going to try to find a way to make it easier and simpler, because that's what we all do. It. Everybody on this thing, we all what a pain in the ass, but we all kind of suffer through it, because if we don't, we're really jerks. Making it really hard on the bad guys is going to make it really hard on the good guys. So that's here. Where's your acceptable pain tolerance for your organization?
It's a cultural thing, right? Each organization is
I mean, yeah, you can throw all sorts of tech at it that makes it a bitch, absolutely, but in order to get to Google Drive, you don't want to have to walk through, get to Fort Knox, and then you're going to automate it. All right, if you automate it, then you got another single point of failure. Well, then you're going to put another feedback loop with a secondary identification. That's 2FA. Oh, no, screw 2FA. Let's do 3. No, let's do 4FA.
Right. So a good example of that is making the requirements for passwords too onerous. So you've got people putting pieces of paper on their computer with their password on it. So if anyone happens I'm going to call bullshit on a lot of that. Okay.
Because I was teaching security a long time ago, and the whole complex password thing is, again, probabilistic. So I decided way back then, in I guess mid-90s, I mean, we all had 15 passwords in 1995, right? It was like, that was too many. And so I said, I'm going to come up with an algorithm. So I wrote an algorithm, and it's one in my head. That's it, one algorithm. And every one of the passwords that I create using this algorithm always gets the really strong, and I never forget my passwords. There are ways to do it.
Well,
maybe I'll write a book on it. Right?
I think we're all hopeful of the day when we never have any passwords, and I think there's a lot of movement towards that. You think that's coming soon, or is it still years away?
Nothing is going to happen tomorrow.
Yeah.
It's what's the next priority going to be? Who Josh Ma just? Oh, Bob, you're welcome. I didn't have an answer. That's why. Josh Ma says, if trust is the inverse of risk, does zero trust architecture equal 100% risk architecture? I love the way I really wish I had my semantics at my fingertips right now, but I think that I have a smart ass answer and I don't know what it is. But no, I see where you're going with it, and there's zero risk. I like that. Do I have to fix that? No, I'm not going to fix it. I'm going to find an answer that's called. But no, I get it. I hear what you're saying, and thank you. Cool. That makes me. I got to go fix something or think about it now.
No, it's a clever post. Thanks, Josh.
It really is.
Yeah, Brian Schultz.
I love getting called out while I'm speaking.
All right, you can think about that. Brian Schultz, who's actually a former ISSA International Board member, has a question for you, Win. Fundamentally, we lack trust across all platforms. Too much anonymous influencers and influencer bots, such as nation state. Thought on a digital ID to give high confidence of the source of information so we can weigh the level of truth based on its source.
Believe it or not, this was a conversation that we began in roughly 1990-91 when the internet was going to be this freedom. It's going to be kumbaya for everybody. And the argument that we security folks had was that to build, the internet's going to build and it's going to grow. We should have some sort of digital ID for verification. And that's when PGP came out. And there were some different kinds of approaches that were done that were a pain in the ass and were never obviously adapted. And on the other hand, the argument was, oh, the internet should be free, information free. And we had not envisioned, other than the Russians did envision, we did not in our culture, what the anonymity and crowdthink effects were going to be 30 years later. So I absolutely am a fan of having a secure zone, if you will. I mean, there were different terms that we threw around back then. And it's like, if you want to come down to my house, I got to really know who the hell you are. And I'm not against that. I think anonymity has its place, but boy, you know, I would love to make the argument that Facebook should not have. You should have verification, almost to the point. You know, you can't open a bank account, you can't trade Bitcoin, you can't do any of that stuff without some level of verification. And I could make the argument that there's so much hostility out there. What's wrong with ID? And if you want to go have a hostile zone, go have a hostile zone. Be cool, but I just don't want to go to that, and I don't want you in my sandbox. And I don't want that to ever, though, become internet balkanization. So, yeah, not an easy question, but yeah, I'm for it.
We got a question from Joe Farhood, totally changing the subject, but an important aspect of security. I want you to elaborate on the human factor in security.
I really like to think abstractly. And so all of the work that I've been doing on probabilistic security, analog security, yada, 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 I call ACK, A-C-K, anthro-cyber-kinetic security, because there are three fundamental domains that exist. We have the physical domain, define it however you want. We got the cyber domain, okay, human domain, and they all cross over a little bit, but you could also view them in stovepipes if you choose. So I would argue that all of the principles of analog security and all the other stuff I've been talking about work in all three domains. Look at, for example, I will get to human in a second, trust me. Look at the greatest ICS project on the planet. The largest ICS project is the Delta Works in Holland. And in 1953, 40% of the country got flooded. Both parties, 3 months later, funded this amazing piece of engineering that's still being constructed, which protects Holland from the North Sea fundamentally. And it is, take a look at the ICS, the engineering, how it all works. So that is all absolutely analog too. Now, humans are fundamentally analog creatures. That's what we are. We are not digital, which is part of the problem we have with security and computers, is that when we see an answer 10.324, our brain doesn't quite compute that. It takes longer to compute that than it would be on a percentage, on a analog scale. Somewhere greater than 10, not quite 11. Okay, close enough. Clocks, analog clocks. It's faster for the human brain to process an analog clock than it is a digital clock, because we have to convert the whole thing. So it's another 50, 80 milliseconds of wasted time. So when we look at humans, we have to consider how they are as a detection reaction circuit. And that is all about sensory input. And that sensory input comes in all these various ways, and there's various delays that occur naturally. It's like when you're driving at 60 miles an hour, it's going to take 120 milliseconds if you're alert to get your foot off the pedal over to the brake pedal. Okay. And if you have 2 drinks, it takes 380 milliseconds. And same thing with all of our senses. So when we combine ourselves into this system of us with a computer and maybe some mechanical device, kinetic thing on the side, it's exactly the same in terms of the calculations. It's still, you can measure it. My parent company, I'm not plugging it all, but the fishing companies out there, they have ways of measuring performance over time. And that becomes an issue, a mathematical issue of normalization of data between 2 disparate systems. And the math and statistic guys know how to do this. So I would argue humans are the same as machines and everything else in terms of the calculations and figuring out how this all works. And then you add in influence, and but that becomes a whole different OODA loop, doesn't it? Does that answer your question?
Well, Rob actually added another comment and question on the human element. He's been seeing a lot of different universities and companies talking about apprenticeship-style programs for cybersecurity. What would you say to them are the most important skills to develop, and how best to go about it?
I actually wrote a long paper on that. I don't think I've published it yet. When people are being trained for cybersecurity, they're being trained, learn TCP/IP, get your CISSP, know your digitals, and then they go from there. So they get this construct. So what really got me going, it was a number of years ago, I was giving a talk on early analog stuff, and I was talking about Shannon. All right, show of hands, who knows Shannon? Okay, not enough. No offense. Because Shannon is the founder and definer of information theory from the 1940s and 1930s. And he worked with von Neumann developing the very foundations of the industry we are in. So we don't teach history. We don't teach the history of conflict, of warfare, because this is warfare, as I've been saying since my book, 35 years. This is war. Why don't we teach conflict? Why don't we teach the history of how we got to where we are? Good, bad, indifferent, not necessarily with indictments, but there's a storied history here because we keep making the same frickin' mistakes over and over and over again. I mean, honestly, we're doing the same stuff all over, and that means we haven't studied history. We haven't decided that that is the classic definition of insanity. And so we're teaching the same stuff over and over again. We're doing the same stuff over and over again because we're not teaching the history. Also, we don't teach interdisciplinary engineering skills, fundamental engineering concepts and systems analysis. That has nothing to do with cybersecurity, except it's the foundation of everything that we do. And we don't teach basics, foundations of engineering, computer science, and again, how we got to where we are. Then the third element I would absolutely add into, not because of the question, but it's absolutely believe, is understand psychology. We have been designing all this crap now for 70 years and trying to get the human to adapt to the cyber. Aren't we smart enough to try to get the cyber to adapt to the human? Why did it take so long for visualization techniques to become important? We need to teach these guys that it's a human experience, not a computer or technical experience that this is all about. So that is where I would absolutely put some serious curriculum in. They don't need to be experts at all, but damn, they need to be aware of it to some level of depth.
All right, and history is important. Listen, on that note, we're at our time. It's been an enlightening talk. I do appreciate it. I always love listening to you speak, Win, and I thank you again for joining us.